Hello everyone, welcome to the lecture series of KE 053 subject code, and the subject name is VLSI technology. This is the 12th lecture in this series and we were discussing the oxidation techniques, and one thing more, that these all lectures are interconnected to each other. So if you are new to this lecture, you should go to the previous lectures as well as. So the topic which we are going today is oxides and oxidation techniques in the system. That what are the oxides which we are going to form with the help of oxidation technique, and what are the various oxidation techniques that we can use in the system. So the first very basic oxide, we know that in the previous lecture we have covered that in case of silicon, we have grown the silicon dioxide layer, right? We have seen that the silicon dioxide layer is grown over the silicon substrate, right? This is silicon dioxide and it is grown over the silicon substrate. And as per the Deal grooves method, we have seen that how the silicon is taken from the silicon substrate itself, and some portion of the oxide layer is grown inside the silicon and some portion is grown on the top of that substrate with the help of oxygen or water molecules, right? So when this SiO2 is formed over this silicon, it has some property. It has a very good, it behaves as a very good insulator. It has the resistivity 1 is to 10 raised to the power 20 ohm centimeter with the energy gap of 9 electron volt. It has a very high breakdown electric field, which is 10 megavolt per centimeter, and we can produce we can have a stable and reproducible SiO2 interface. This is the SiO2 interface, right? We have the very stable interface in case of this silicon dioxide, and the conformal oxide growth on exposed silicon surface can be obtained, right? So when we have the thermal oxidation, we have the substrate silicon dioxide, some form of the silicon dioxide is already grown, and then we grow the over this silicon, we have grown this silicon dioxide, right? And this silicon dioxide is also used as a very good diffusion mask for the common dopants, right? So in the next process, in the upcoming process, when we are forming the, for example, we are forming the NMOS, we have to form the NMOS, we take p-type substrate, okay, and we must have here N plus areas. Okay, these N plus areas are formed with the help of diffusion or ion implantation. These N plus areas are formed with the help of diffusion or ion implantation. So when we diffuse some dopants in the substrate, we must have some window, we have to create some window, and like we have created this window, some portion of the oxide layer is removed from these areas, and then the dopants are added to these areas, so that we can have this N plus region, substrate and drain. So this SiO2 behave as a very good mask for the upcoming processes, that is your ion implantation and diffusion. And the very common dopants which we can use in the IC fabrication are boron, phosphorus, arsenic, and so on. So we have the silicon, and these oxides, these dopants are then passed to the silicon over the silicon dioxide layer, and where we don't have the silicon dioxide layer, they will move inside the silicon, okay. And in the and it behave as a very good etching and selectivity between the silicon and silicon dioxide, right? So because we have to remove silicon dioxide over these areas, we have to remove the silicon dioxide over these areas. So what we do, we dip the this oxide formed silicon substrate to hydrofluoric acid, and then which results in the removal of silicon dioxide layer, so that we can add the dopants to the required areas only. So why the oxide of this silicon is done? Silicon dioxide growth is a key process step in the manufacturing of all silicon devices, right? We have seen in the previous slide that when we form the MOSFET, metal oxide semiconductor, we need to dope some of the atoms, some of the molecules, and so we must have some barrier layer which can protect the rest of the substrate. The thickness of 1 micrometer oxides are used for the field oxide, which is used to isolate the device from one to another, right? Because we are talking about VLSI technology, and in VLSI technology we have to form n number of MOSFETs over a single IC, single wafer. For example, we have this first MOSFET and second MOSFET, right? We have the gate over, right? We have the gate 1 and gate 2. We have some MOSFETs which are fabricated on a same substrate. So to differentiate these two MOSFETs, we have to form some partition. This partition is done by this thick oxide, which will prevent the working of one MOSFET to another MOSFET, so that the characteristics of one MOSFET should not interfere the characteristics of another MOSFET. Okay, and this thin oxide, thin gate oxide, that is 100 Armstrong, is used in MOS devices. Here we use a very thin layer of oxide, that is 100 Armstrong. The width of 100 Armstrong is used to form the gate oxide. The sacrificial layers are grown and removed to clean up the surface. The stability and ease of formation of SiO2 was one of the reasons that silicon replaced the germanium in the semiconductor industry, because when we grow the silicon dioxide, it takes much less time as compared to germanium, and when you go for the oxidation of germanium, it will take some little more time to grow the germanium oxide. So what basically oxidation process, we have also seen in the few lectures, in the few last lectures, that oxidation is a chemical process of silicon reacting with oxygen to form the silicon dioxide. Okay, to grow this oxide layer, epitaxial wafer is heated to a high temperature of 1000 to 1200 degrees C. So the process is carried out at a very high temperature, that is, so the process is carried out at a very high temperature, that is from 1000 to 1200 degrees C. The heating is done in a very clean furnace, because even a small amount of contamination will lead to some changes in the silicon properties, right? And this step is true for all the processing steps which are carried out in the IC fabrication technology. The oxidation process can be done as a dry oxidation and wet oxidation. In case of dry oxidation, the oxide is introduced as a high purity gas and has a better electrical characteristics. And in case of wet oxidation, it is introduced as a water vapors by chemical vapor deposition process, and the chemical reactions involved are silicon plus water molecule. We are going to have silicon dioxide plus hydrogen molecules as a residual. Okay, so this wet chemical oxidation process is a very much fast process. The oxide layer grown over with the help of this wet oxidation process is very fast. The layers are thermally grown. Excellent insulation property will be there. Dielectric constant of silicon dioxide is about 3.9, and it is used to form the capacitors also. So some applications of this SiO2 layer in the VLSI industry, it is used as a masking, right? We have seen that it is used as a masking in the implantation and diffusion process. It used as a surface passivation to avoid the interference between the n number of devices. Electrical isolation, as a electrical isolation it is used, device isolation, and gate oxide material in case of MOSFETs, right? So several techniques for the forming of oxide layers have been developed, such as the first very basic technique is the thermal oxidation, which include the rapid thermal technique. Then we have the wet anodization or oxidation, vapor phase technique, that is known as a CVD technique, commonly known as chemical vapor deposition technique. So when the interface between the oxide, depending upon the application, we can select any one technique. So for example, when the interface between the oxide and the silicon requires a very low charge density, then the thermal oxidation has been preferred. Okay, so when the charge density between the silicon, we have the silicon and the silicon dioxide. Between this interface, we need to have a very small charge density, then the thermal oxidation technique is used. When the oxide layer is required on the top of the metal layer, in case of multi-level metallization structure, the vapor phase technique is used, and thermal silicon oxidation is the principal technique that is used in the IC fabrication technology. So what we have seen that the oxidation techniques can be thermal oxidation and rapid thermal oxidation. Under this thermal oxidation, we can have the wet oxidation technique and dry oxidation technique. For the wet oxidation technique, when your solid silicon is reacted with the water molecules, we are going to have the silicon dioxide as a solid and hydrogen molecules as a residual. And in case of dry oxidation, we have the silicon solid, oxygen gas is passed inside the chamber, and then the silicon dioxide will be formed. Okay. So some advantages and disadvantages and the difference between the two, that in case of wet oxidation, in case of wet oxidation, the a stream of water molecules is passed inside the chamber, and then the water molecules will react with the silicon to form the silicon dioxide. Whereas in case of dry oxidation, pure dry oxygen is required to form the silicon dioxide. Okay. Hydrogen, in case of if you check the drawbacks, here we have the hydrogen atoms as a residual, which is liberated by the decomposition of water molecules, which produces some imperfection that may degrade the oxide quality. And in case of dry oxidation, it is a bit slow process. That is the only drawback with the dry oxidation process. It is a very slow process. Okay. In case of wet oxidation, it is carried out at a very fast speed, and the oxides which we can grow with the help of wet oxidation are the thick layer oxides that are used to protect two devices between the on a single IC. If you check the advantages of this dry oxidation, it provides a very uniform layer. Relatively few defects are there, and it has a very low surface state charge, and thus makes an ideal dielectric for the MOS. So we have seen that in case of MOSFET, we need to have a very thin layer. So that thin layer in the range of some 100 Armstrong, that thin layer is grown with the help of this dry oxidation process. Okay. So with the help of wet oxidation, this process is carried out at 900 to 1200 degrees C, and with the help of this, we are going to have the less than 2.5 micrometer thickness of oxide. It behaves as a good insulator. Field oxides can be created with the help of wet oxidation, and it is used as a masking process. Whereas in case of dry oxidation, it is carried out at 900 to 1200 degrees C, generally between 1000 to 1200 degrees C. A very thin layer of oxide is grown, that is between 0.05 to 0.5 micrometer. It behaves as an excellent insulator, and it is used as a gate oxide. So let us check the systems which are used to grow this oxide layers. So the very first system under this thermal oxidation is we have this furnace. We have this horizontal furnace where your wafers are placed vertically. Okay, so this is the example of your horizontal furnace or chamber or reactor. Okay, so we have this quartz board. Over this, your wafers are vertically placed, and here we can see that we have this hydrogen gas, oxygen, nitrogen and HCl gas. Depending upon the requirement, we are going to pass the gases one by one. So heat is added to the oxidation tube during the reaction between the oxidants and silicon at 700 to 1200 degrees C temperature, and the range of oxide grows inside this chamber as the temperature grows. So it is used, this chamber is used to grow the oxide between the 60 to 10,000 Armstrong. Okay, and from this side we are going to have the exhaust gases. So how basically these gases are passed? First, the nitrogen gas is passed inside the chamber, because when we load the wafers, when we load the wafer tray inside the chamber, there should not be a oxygen molecules, right? And we know that in case of VLSI technology, the removal of oxygen molecule is one of the toughest process. So a very small amount of oxygen will react with the wafer, and they will form the oxide layer before actual oxidation process starts. Okay, so before oxidation starts, we pass the nitrogen gas inside the chamber. It behaves as an inert gas. It will not allow the nitrogen molecules to react with the silicon, and when this temperature is achieved, then only your oxygen will be passed. Now let us check the theory part quickly. So your wafers are chemically cleaned. So before placing the wafers inside the chamber, we have to clean the wafers. That is the first requirement in any process. So wafers will be cleaned, dried, and then placed in the loaded station or a paddle or a boat, right? In case of that, we have the quartz boat. Then the dry oxidation is introduced in the chamber, and nitrogen prevent the oxidation formation occurring, right? So before actually applied the O2 molecule, there should not be any oxidation process. So for that, your nitrogen gas is passed. Nitrogen gas flow shut off and the oxygen added to the chamber when the furnace has reached the maximum temperature, that is your 700 to 1200 degree C. So when we achieve this temperature, then only a nitrogen will be stopped and the oxygen supply will be started. Nitrogen gas is introduced in the chamber again to stop the oxidation process, and then wafers are removed from the surface and it will be passed for the inspection. So under this technique, the oxidation technique chosen depends upon the thickness and the oxide properties required. Okay, oxides that are thin and that require a very low charge at the interface are typically grown under the dry oxygen, in the presence of dry oxygen, and where the thickness is greater than 0.5 micrometer, steam is used and it is carried out as in wet oxidation. Okay, higher pressure allows the thick oxide to grow to be achieved at moderate high temperature in the reasonable amount of time. And 1 atmospheric oxide growth, the most commonly used technique, is typically carried out in the horizontal diffusion tube, although the vertical diffusion furnace are more useful in today's time. So in certain system, the wafers can be rotated to provide the better uniformity, right? The wafers which are placed inside the furnace, they should be rotated so that we can have a better uniform growth over those wafers. These systems provide the excellent thickness uniformity and low partial density, and the coated temperature uniformity range is plus minus 0.25 degree C to 1 degree C, with the oxide uniformity of plus minus 1%. And in some system, the heating element can be moved relatively to the wafer so that we can allow the rapid cool down process. The wafers in the vertical systems are usually supported at a 3 or 4 points or fully supported around in the most of the periphery, right? If you have a vertical furnace, some furnace like this, suppose we have this furnace like this, and we have this boat, some boat is there, and here your wafers are placed. Okay, the gases will be passed from this side. Okay, the reaction gases will be passed from the top side, and then the oxidation will be carried out. So most thermal oxidation is performed in furnace at a temperature between 800 to 1200 degrees C. A single furnace accept many wafers at a time and a specially designed quartz in a quartz rack. This board entered the oxidation chamber and held the wafer vertically beside each other. However, many modern design holds the wafer horizontally, as I shown as I draw in the previous slide, and below each other, and loaded them into the oxidation chamber to form the oxidation, right? So now what basically is the difference between the vertical chamber and the horizontal chamber? So when we place the wafers in a horizontal chamber in a vertical way, okay, so the contamination will be passed to each wafer. But in case of horizontal, in case of vertical furnace, when your wafers are placed like this on the only the contamination will be placed on the top of the wafer only. Rest of the wafers will be contamination free or will have the very least contamination. So vertical furnace stands higher than the horizontal furnace, so they may not fit into some microfabrication facilities. However, they help to prevent the dust contamination, unlike horizontal furnace, in which the falling of dust contamination contaminate any wafer. Vertical furnace only allow it to fall on the top of the wafer, right? So the vertical furnace also eliminate the problem present in the horizontal furnace, such as the uniformity of growth oxide the wafer. Let us check how it is removed. So in case of horizontal furnace, we have the convection currents, right, inside the tube, which causes the bottom of the plate. See, the plates are formed like this. The plates are placed like this, and we have the convection current inside the chamber, right? So the bottom of the tube will be slightly colder than the top of the tube. Obviously, we have the convection current over this side, temperature will be slightly more than the lower side, right? So as the wafers lie vertically in the tube, the convection and the temperature gradient with it causes the top of the wafer to have a thicker oxide than the bottom of the plate. So what we are going to have here, we have the more thick oxide, and this side we have the some oxide like this. So uniform oxidation process will not be carried out in case of horizontal furnace, okay. But in case of vertical furnace, this solve the problem by having the wafer sitting horizontally and then having the gas flow in the furnace flowing from top to bottom, significantly dampening any thermal convection. Vertical furnace also allow the use of load lock to purge the wafers within nitrogen before oxidation to limit the growth of native oxide on the silicon substrate. So in this case, the horizontal furnace, the wafers are held vertically in a slotted paddle board. Typical oxidation temperature range is from, we have seen that it is 700 to 1200 degrees C, and the uniformity achieved is plus minus 1. In the standard procedure, the wafers are chemically cleaned, dried, and then loaded into the wafer. So we have seen this, also seen this dry oxidation and wet oxidation process, and during this dry oxidation, the process tube where it is react with the silicon, the dry oxidation is a slow process. It grows the film at the range between 140 to 250 Armstrong per hour. It is only used in the industry to grow the thin oxides, okay. It is only used to grow the thin oxide where your device length is less than 1000 Armstrong. In case of wet oxidation, it is a very fast process, okay. The water molecules are small in size, and then the oxygen molecules, they diffuse the faster in the silicon, and the growth rate is fast. The wet oxidation rate is carried out at 1000 to 1200 degrees C, and it is used to grow the thick oxide. So these are the pictorial representation of this dry oxidation technique. Under this dry oxidation technique, we have the silicon atoms, right? Oxygen molecules will be diffused inside, oxygen diffused through this oxide and will form the silicon dioxide, okay. We have this high pressure dry oxidation furnace. It is an example of horizontal furnace. We have the nitrogen gas which is passed inside the chamber first, then then when the temperature of 700 to 1200 degrees C is achieved, then only this will be stopped and the supply of oxygen will be started. Here we can see that wafers are placed vertically and we have some pressure valves, and this, it is known as quartz tube. It is a heater to provide the proper heating, and so that's the proper temperature can be maintained. Okay. The dry oxidation system with HCl, sometimes HCl gas is also used in the system. So we have this nitrogen process, oxygen and HCl. We have this wafers placed in the circuit, and from this side we are going to have the exhaust gases. Then the thin oxide, growth of this thin oxide. Thin oxide is grown when we have the very small feature size for the formation of gate in case of MOSFETs. The addition of chemical species to oxygen decreases the oxide rate. So HCl and trichloroethylene and trichloroethane can be used as a reactant molecules also. So decreasing pressure slow downs the oxide growth rate. The oxidizing ambient may also contain the several percentage of hydrochloric acid. The chlorine removes the metal ion. They may occur in the oxidation process. The thin oxide growth must be slow enough to obtain the uniform layer over the silicon substrate. So this is the diagram for this when we use the same HCl. It is HCl here. We can see that it is used. The chlorine part is used to remove the metallic contamination inside the chamber. Then we have the wet oxidation. Here the wet oxidation, we have the water molecules. They are reacted inside over the silicon substrate. We have the silicon, right? We have then the hydrogen molecules will be liberated and the oxygen molecules will react with the silicon to form the silicon dioxide. Okay. So the function of these oxide layers we have already seen. It is behave as a passivation to protect the wafer from scratches and particle contamination. It traps the mobile ions in the oxide layer. Next, masking. During the diffusion or ion implantation or etching, it is used as a masking. Insulating gate material. It behave as a insulating gate material. Very thin oxide layer is grown over the silicon. It allows the inductive charge to prevent between the gate metal and the silicon. Then it can work as a dielectric material, and it can work as a dielectric material for the tunneling oxides also. Okay. So here we can see that we have the silicon dioxide. It behave as a mask, right? So that the dopants will be diffused here only. It will not be diffused under this side, right? Here it is used as a field oxide. Here it is used as a gate oxide, right? This gate oxide. Okay. So the thickness level for each application is different. For field oxide, it is used as 1 micrometer. For masking oxide, it is 0.1 micrometer. For pad oxide and gate oxide, it is 10 nanometer. The chemical oxide from the cleaning and native oxides, it is 1 nanometer. Then this deposited oxides, we can have the deposited oxides which behave as a masking oxide. Then under this wet thermal oxidation technique, a flash system is used. Under this flashing system, an automatic flat silicon surface can be produced by flashing or heating rapidly between the 1200 degrees C. Even though the silicon melting point is around 400 degrees C, its surface may start and it will melt around 1150 to 1200 degrees C in a ultra high vacuum conditions, right? So we have this hot plate. Here we have the water molecule, carrier gases will be there, and then it will be passed through the system, and then we are going to react. They are going to react with the silicon to form the silicon dioxide. If we are using the wet conditions, we have this hydrogen and water molecules. So some additional chemical processes which are used in the oxidation are anodic oxidation process. Wafer is attached to the positive electrode. It is immersed in the potassium nitrate. Then immersion tank contain the negative electrode. Oxidation will be done when the current is applied and the reaction between the silicon and oxygen will occur to form the silicon dioxide layer. Then the characteristics of this process is the oxidation reaction occur at the surface of the oxide silicon atom and move to the top of the oxide layer during the oxidation. It is used to grow the oxide layer on the wafer that will be tested for the dopant location and the concentration. This is the diagram, pictorial representation of the vertical furnace, vertical tube furnace and horizontal tube furnace. This is the vertical tube furnace and this is the horizontal tube furnace for the used in the actual foundries used for the oxidation process. So by this we have completed the oxidation process. We have seen that how many reaction chambers are used, how the reaction chambers inside those chambers, how the reactions are taken place, what are the properties of silicon dioxide and what is the need of this silicon dioxide, right? So thank you so much.